last talk is about three-dimensional dual camera system for in-situ lunar and planetary surface exploration.
Good afternoon, everyone. My name is Nayeon, and I'm a graduate student at Kyung University in South Korea. This study focuses on developing lightweight and high-resolution optical system for analyzing microstructure of lunar or planetary regolith directly on the surface. This is the outline of my presentation. And lunar and planetary exploration, high-resolution in-situ 3D observation remain limited because sampling often disrupts the native microstructure. To overcome this limitation, we propose a compact and lightweight 3D microscope based on innovative optical elements and optical system design. Additionally, a 3D camera is integrated to assist with microscopic focusing and provides supplemental terrain measurements. This is our period configuration. The DFP camera, 3D camera, along with the projector, is oriented toward the microscopic imaging camera. Lunar surface particles are exposed to solar ultraviolet radiation and solar wind, which electrically charge the regolith. Under such conditions, the particles are weakly bonded, and the regolith is expected to develop three-dimensional microstructure called fairy castle. Apollo missions demonstrated that the lunar dust caused aberration, human health issues, and mechanical interference. The space impacted mission operation and data quality. Therefore, understanding the properties and behavior of lunar dust is a key requirement for future surface exploration systems. Recently, China successfully conducted lunar sample return missions through the Chang'e program. However, collecting and returning samples may disrupt the microstructure of particles. Therefore, our approach aims to observe lunar or planetary surface particles directly in situ. Lunar regolith research has moved from ideas and models in the 1960s to theoretical interpretation and sample analysis in later decades. Now the focus is on combining remote sensing, lab analysis, sample return, and in-situ observation. So our 3D regolith period development team consists of 3 research groups. And the 3D microscopic camera system utilizes the vortex beam. A vortex beam is a unique type of light wave with a helical phase structure. And it contains the phase singularity at the center, resulting in zero light intensity at the beam source. And the spiral phase plate is the commonly used device for vortex beam generation. To obtain a spiral phase contrast imaging, the optical system must guide both the high-order diffracted beam and zeroth-order undifracted beam along defined paths. Then it can operate as a spiral interferometer. In this spiral interferometer, the surface of the sample causes a spiral fringe patterns to appear in the image. The spacing and orientation of these fringes contain information about surface slope and height. This allows the 2D spiral pattern to be converted into a 3D surface model of the sample. So, spiral interferometry offers several advantages. It enables quantitative height measurement and of the target, and its self-interfering design employs a simple single interstellar, which contributes to a more compact system. Additionally, it is more stable against optical misalignment. And concave and convex shape can be distinguished by the rotation direction of the spiral interference fringes. And reflected optical system can be categorized into on-axis systems, co-axial open-axis system, and confocal open-axis systems. And we use a confocal open-axis system in which the mirror shares the common focal points, effectively removing the obstruction and linear astigmatism. And the linear astigmatism free system then uses 3 mirrors is called LAFTMS. So the design LAFTMS functions as lens 1 and lens 2 in the spiral interferometer. As a result, the two identical LAFTMS units are arranged symmetrically, facing each other. So target LAFTMS, SPP, LAFTMS, and detector. This figure shows the rough automechanical design. The system is approximately 1.5 kg and has a volume of 2U. U is the unit of cube set. The topographic imaging camera employs the principle of digital fringe projection. Digital fringe projection is an optical measurement technique that projects fringe patterns onto an object and analyzes their deformations to rapidly and accurately obtain its 3D shapes. So this figure shows the process of obtaining 3D shapes data using DFT. And this figure shows actual 3D imaging results of sand and cement materials. And this is another experimental result demonstrating high precision 3D imaging of footprints preserved in sand or soil. Then this setup helps focus the microscope camera and allows for observation of the surrounding terrain. This is the operation sequence for observing lunar and planetary surface with the integrated system. First, the DFP system scans the wide area in 3D. Next, the region of interest is placed within the microscope's depth of field using the DFP data. Then the focusing is performed using a piezo actuator. Finally, high-resolution microscopic imaging is conducted. And this is the flow chart summarizing the mission operation process of the payload mounted on a rover. In conclusion, we propose 2 key payloads. The first one is the spiral phase contrast microscopic imaging system. This system enables fine characterization of surface particles at the microscopic scale. The second one is the DFP-based imaging system. This system allows microscope focus adjustment and 3D observation of the surrounding terrain. So we propose to integrate these 2 payloads. Such multi-scale observation have revealed the relationship between particles and terrain and improved the reliability of sampled data. Currently, we are working on developing a prototype model, and in the future, we plan to propose this system as a payload candidate for South Korea's 2032 Lunar Lander and Rover mission. Yeah, thank you for listening.
Thank you very much for your presentation. Do you have any questions?